Hi students, Professor Nugent here. In this video, we're going to discuss multicollinearity. There are two types. The first type is perfect, which is a big problem, but easy to fix. The second type is imperfect. Perfect multicollinearity arises when there is a perfect linear relationship among the independent variables. Often this happens because a researcher has included, for example, a variable in thousands of dollars and a variable in millions of dollars unknowingly. And the, the way to solve that is just to exclude one of the variables. Imperfect multicollinearity arises when there is an imperfect, albeit close, linear relationship among the independent variables. So let's try to characterize this a little bit more carefully. If we add to our assumptions homoscedasticity, then we can write the variance of our estimator of beta j as sigma squared over the total sum of squares of j times 1 minus r squared j, where r squared j, this is the coefficient of determination from a regression of xj on the other independent variables. So observe that the level of the linear relationship between xj and the other variables is going to matter for the variance, which is the consequence to imperfect multicollinearity. If you have a high r squared j, then you're going to have a higher variance. A lower r squared j means a lower variance. If your r squared j is 1, in other words, if your xj is a perfect linear relationship of your other variables, then observe that this term goes to 0, your denominator is 0, and your variance is infinite. So that is when you have a perfect multicollinearity, your variance is infinite. And the key to there is just to drop one of the variables that's causing that perfect multicollinearity. But when it's imperfect, the amount or how bad the multicollinearity is comes in terms of this coefficient of determination, and the consequence is higher variance. Now, why? What's going on? Well, there was the thing that we're trying to do, or rather trying to identify, is this partial effect beta j holding constant the other effects. If there's a strong linear relationship between beta j or between xj and the other variables, then there's not going to be much variation left in xj once you hold all the other variables constant with which to identify this beta j. And so you're going to end up with an imprecise estimate, which is why when this r squared j is close to 1, then this variance is very large. You get that imprecise estimate. Now we can add we can bring in a statistic to give us an idea of how bad that variance inflation is using the variance inflation factor. So this is for imperfect multicollinearity. We can define a variance inflation factor. The variance inflation factor is just a 1 over 1 minus the r squared j. All right, so this is that bottom term in the expression of variance. So some researchers have used a cutoff of, say, 10. When the variance inflation factor is above 10, then perhaps if adding a certain variable caused the variance inflation factor to go above 10, then that cutoff means that it is detrimental to having added that variable. The thing about this variance inflation factor cutoff of 10 is that it's sort of arbitrary. And the other thing is that there are other factors that matter for variance, not just this coefficient of determination. The error variance also matters, as does the total sum of squares in J. So you might end up having a relatively high variance inflation factor, but if you have a small error variance, or if you have a high total sums of squares in J, then perhaps it's not such a bad problem, because you may be able to come up with a sufficiently precise estimate of beta J. Let's think about two more things in terms of this multicollinearity when it's imperfect. We are concerned about the precision of the estimates of the variables of interest, right? Sometimes we specify a model as y equals beta 0 plus beta 1 x1 plus, let's say, delta 1 w1, where w1 might be a control variable. We're concerned about the precision of beta 1 because we're trying to identify our causal effect. Less concerned about the precision of delta 1. So amongst the control variables, we're not so concerned about there being a linear relationship. We're concerned about the linear relationship with respect to x1. So then when we think about x1, we have to evaluate a trade-off. And the trade-off is bias for variance inflation. If this control variable is correlated with x1, then that is going to result in a higher variance of this estimate, beta 1 hat. So that results in our variance inflation by bringing w1 into the regression equation. But if we leave it out, w1 is correlated with x1 and w1 matters for y, then we're going to have bias. So here's a way to think about the trade-off. Variance inflation, or rather variance, generally is going to come down as sample sizes get larger, right? Because your error variance may get smaller, your total sum of squares is going to get larger. And so as your sample size gets larger, you're going to get a more precise estimate of your beta 1 hat. But the bias is never going to go away, no matter how large your sample. So being dinged for bias is much more painful than being dinged for variance inflation. And so typically it may be advisable to assume the variance inflation rather than the bias and bring in the variable that's correlated with your variable of interest. All right, folks, that is it for heteroskedasticity. No, we're talking about multicollinearity. That's it for multicollinearity. Stay tuned to the next video when we will prove the Gauss-Markov